Hello, everybody. Today we're doing Chapter 3, Question 5 in Landau Lifshitz Mechanics. And before we get started, I just want to ask if any of you viewers have any other topics that you would like me to cover or any suggestions for these videos. I enjoy making these problem-solving videos as I'm working through Landau Lifshitz myself. I find it enjoyable. But I would also be interested in making things that you are interested in doing. So with that, let's get started. We're integrating the equations of motion for a particle moving on an inverted cone, the vertical angle of 2 alpha. So what that looks like is the bottom of an ice cream cone where the angle from the edge to the symmetry axis is alpha. Now we're going to identify a point on the surface of this cone and specify it using an angle phi around the central axis and a height z. So with this, we can write our Lagrangian. I'm going to introduce a variable gamma that captures something akin to the slope of the cone. Next, we can notice that the Lagrangian does not depend on the variable phi, which makes it cyclic. It gives us a conserved quantity. That conserved quantity will be the angular momentum around that central axis. So denote that capital M subscript c, and it will be a constant. Now we can solve for phi dot itself in terms of the angular momentum and z and our constants. And we can use this to eliminate phi from our equation altogether. Again, we're going to use the notation of an effective potential, a modified potential, so that we can more easily write our final integrals. And now using conservation of energy, we can write dt in terms of the rest of our expression and dz. Similarly, using our conservation of momentum, we can write dt in terms of d phi and now we can integrate to get t in terms of z, an integral over z, and we'll also be able to arrive at an integral for phi in terms of an integral over z. Very similar to the last problem, we've chosen z as the variable to integrate over because it has clear boundaries. There's a lowest point and a highest point that the particle will be able to reach given a specific energy. And that determines the bounds z0 and z1. Now we can draw this using the diagram from before. We'll repurpose it and depict an example of what this motion might look like. So here we can see the region in which the particle can lie between the two boundaries. If it gets too close to the center, its angular momentum will cause its energy to increase too much. And of course, it cannot get too high due to the gravitational potential energy at play. Thank you for watching, and please share any comments or suggestions below. I'll see you next time.